Okay, so today's simulation is going to be about how to run and set up a cost-effective transient simulation. And that is going to be on our standard CFD solver, so on the OpenFOAM-based CFD solver. My name's Darren Lynch. I'm an application engineer here at SimScale. I'm quite experienced in CFD and engineering design, and I studied aerospace engineering at Brunel University. So I'm going to start off just giving you a little bit of information about SimScale, who we are, where we are, what we do, and then I'm going to move on to the actual topic in hand. So we were founded in 2012. We have some co-founders that created this amazing organisation, and their idea was to basically bring simulation into the cloud on the masses. And really it's just gone from there. 5 years on, or actually 6 years on, we're still standing, and we're creating an amazing product. We've got currently offices in Munich, Boston and New York, and we've got about 80 employees across the globe in 6 different time zones. We've got 150,000 users worldwide with more than 300,000 simulation projects. And a lot of those projects are actually available to you as public projects. So if you have ever been in contact with SimScale, then you'll know that it's got an amazing community. And if you ever wanted to create a simulation from scratch, then you've always got some amazing public projects to really start your simulations from. So that's who we are, but what do we do? So we provide a cloud-based engineering simulation platform, and by that we offer computational fluid dynamics, solid mechanics and thermodynamics all on your browser. So we've got pre-processing, including some CAD cleanup, we've got some meshing, simulation setup, simulation solving, all the way to post-processing, actually getting your results. And that's all done on the cloud in a browser. So there's no hardware setup needed. You just log on to SimScale in your browser and you've got everything there for you. So that's the real advantage of the platform. But I'm hoping some of you that are here today already know that and are very much interested in how to use this fantastic platform to do some transient simulations. So how to use SimScale then? It's in case you're unfamiliar with any computer-aided engineering workflows, you generally start with a CAD upload. So you would create that in your CAD program, be it Onshape, SolidWorks, you choose. Upload your geometry to the platform, and then we go through some simulation setup stages. So we would say, okay, we've got some fluid moving here, or we've got a wall here, etc. And we're also going to do our meshing in that stage as well. And then finally we're going to move on to post-processing the results and analysing the results. So this is the general workflow of SimScale. You upload a CAD, you do your simulation setup, and then you analyse the results, all on the platform. And this presentation does include a live demonstration of this simulation project. So you will get to see the platform in operation yourselves. So today's topic is transient simulation. Okay, and we're going to spend a little bit of time on this slide because we've got to understand actually what I'm addressing. So I'm not going to be addressing the lattice Boltzmann solver, which is our new high fidelity transient solver that's based on the lattice Boltzmann methods. And I'm also not going to be doing any kind of high fidelity transient simulation, which OpenFOAM is also capable of doing in transient. But the things that I'm going to show you how to do are going to be more involved around long period types of transient phenomena. So that might include, so this image is showing a man coughing into a tube, and it's showing the actual cough going out of the outlet, but also its flow in the domain as well. So this kind of simulation application is what I'm going to be showing today, and that might include things like transient thermal buoyancy. So that can be very unstable. You can analyze that transiently. Mixing. So if you wanted to analyze how two fluids were mixing together, then you could apply this technique. And also, it could also apply to some sort of vortex shedding, some oscillations that you're going to see in your fluid domain. And finally, the last thing that it could do for you is essentially, if you wanted to set up some sort of transient boundary condition, you could analyze how that transient boundary condition is going to affect your CFD results. So these are all things that that you could apply this webinar to. As I said, it's the standard CFD solver, not the LBM solver, and it's running transient. And most of our solvers, our standard solvers, are able to be run in transient, whether that be incompressible, convective, compressible. Most of these standard solvers are all available to be run in transient. It comes on to the question, what is a transient simulation? Why do we need it? Well, typically we have two types of simulation. We've got steady-state simulation, which we assume that the results are going to accelerate towards a steady state. By that I mean, if you were to drag an aerofoil through the air, you're going to measure the lift on it, and eventually it's going to get to the point where you're going to say, okay, it's steady at some sort of lift. And that is a steady state. It has reached a steady state. It's not going to change over time. But a transient simulation is something that is going to change over time. And we are interested in the results that change over time. So we could say, for example, that we were going to have a look at something that was typically steady state, but we want to know how it gets there, how the flow develops around this object to reach that steady state. An example of this might be turning on a chip in a PCB. You want to know how the air flows around it. You turn the chip on, and how does the air start to flow around that chip and cool down the design? And it's that time-dependent result that you could analyze. Okay, it's going to reach a steady state eventually, but that's not what we're really interested in. What we're interested in is the journey it takes to get there. Another typical scenario might be if you were to have a domain initialized in a different way, and you wanted to see how it kind of mixes together. So in this example that I'm talking about today, we're going to be looking at a mixing tank where you've got a different fluid in the top half to the bottom half. You've got a impeller, and you're going to mix those two fluids together. And it's this mixing that we're going to be analysing over time to see how it sort of converges to a mixed state. It will, of course, reach a steady state eventually, but that's not what we're interested in. We're interested in how the flow progressed and how it is then going to mix those two fluids together. So the outputs that you're going to get from the simulation, from a transient simulation, are time-dependent results. So it might be fluctuations, it might be an increasing temperature, for example. This might be dependent upon your scenario. But if it's fluctuations, then that could be things like oscillating flows over an aerofoil around a building, and that kind of application. And what we're going to be concentrating on in these simulations is URANs, so unsteady Reynolds average Navier-Stokes. So that is a turbulence model that we tend to use for Reynolds average Navier-Stokes for steady-state simulations, but the unsteady version is what we're going to be using to see these unsteady effects. So the next few slides I'm going to take you through is going to be on the simulation setup, and that is specific to the simulation platform, based on recommendations from OpenFOAM documentation. I'm also going to show you a small article that I wrote a couple of years ago that you can refer back to. So if you guys wanted to go and try any transient simulations yourself, and you wanted to know a bit more detail about the technical aspect of these the algorithms and the theory behind it, then you can of course check that article as well. So without any further ado, we're going to start with step one. So we come to the SimScale platform. What do we do? So first thing, of course, we want to do is we want to upload a CAD geometry. And in this case, it's a fairly simple CAD geometry. It consists of a tank, that's our mixing tank. So remember before I said that we're going to have some fluid in the top, some fluid in the bottom. And we're going to spin this impeller until the two fluid mix together. So what we have represented in the geometry is the mixing tank itself and the impeller, which are both in grey. And also what we've done is we've added a rotational geometry, which is that little red cylinder. And when we come to setting up the simulation, that little red cylinder is actually going to be our rotating zone. So that is how we tell the simulation software anything in this region is going to be spinning. And we're going to define some setups, which I can show you on the platform later. So that is an overview of the CAD. And next up, what we're going to do is we're going to move on to meshing. So meshing is very typical of any computer data engineering analysis. We want to discretize the domain into smaller pieces so we can solve the problem. In this case, for CFD, SimScale, we tend to use the hex dominant mesh type for anything with rotating zones. This particular geometry was quite coarse. It had 273,000 cells, so SimScale platform can typically on the OpenFrame solver deal with up to 50 million cells. So this is quite a coarse mesh, but we've been very particular. We've refined on the blades. You can see a little excerpt there of what the refinement level is on the blades. And we've also split off the cell zone for that rotating part. Now, this is actually quite relevant for reasons I'm going to explain to you in a bit. However, what we generally want to do for a transient simulation is we want to have the cell size as uniform as possible throughout the domain. So what we can actually see here is all of the cells in the fluid tank itself is pretty uniform. They're not really changing. The only time we've ever gone any finer is on the rotating parts, and that is something we can't avoid. You know, we've got to have that level of refinement to capture that detail. However, if it was avoidable, then I would have avoided it, of course. But I'll talk more about that when we discuss some of the simulation setup parameters. So just discussing the initial conditions, I think that was the main part of this simulation was basically telling the solver what it was like in its time zero state. So before we started solving, before we started mixing, what was what fluid was where, and what was the flow like within the domain. So SimScale's got quite a few settings that allow us to be very smart about this. But one of the essential things is that the flow field was initialized using potential flow. So to get some early stability and to speed my simulation up a little bit, time step 0 was given some sort of flow field that used potential flow to initialize it. That's incredibly handy, and that's also available on most of our standard CFD solvers. So if you are setting up a transient simulation, I would recommend using that to just to give you some good initial conditions. What that does mean, however, is that you are starting with some sort of fluid flow field. So you haven't got an entirely stagnant flow to begin with. If you are interested in looking at a flow field from absolutely stagnant, then you would not use this parameter. But it wouldn't affect your results that dramatically if you were to use it. It depends what you're interested in. So the passive scalar is what we use to define the two fluids. What we said here was that we've got two fluids. They've been poured into this tank and they are of similar density. So we can assume the density not to be different. One is not going to be more buoyant than the other, so there's not going to be any buoyancy effects due to density changes in the fluids. But what we've done is we've added a passive scaler to kind of trace where these two fluids begin and end. So we've put a passive scaler that is equal to a fraction of 1 in the top half and equal to 0 in the bottom half. And because this was initialized 50-50, what we would actually expect to see when this becomes a fully mixed tank, then we would actually expect to see the scalar converge to a fraction of 0.5. So perfectly mixed would be 0.5. Hang on, I've got a question. 1 second. So I've got a question that says, are you talking about transient cases in data centers? It depends on what you want to find out, but I would say that these settings would be applicable to you if you were analyzing data centers. So for example, if you wanted to see what kind of transient effect you get from turning some server racks on and off, for example, then that would be equally applicable, yeah. I will go through some more limitations later if I've got time, but generally speaking, yes, I think this applies to you as well. So we were just talking about how the this fully mixed tank would converge to a fraction of 0.5. So that is what we're going to be expecting towards the end after it's gone through this mixing process. And when I show you the results later, you'll see how realistic this actually is. We're going to get a little bit technical now, but not too technical. We're going to start talking about the simulation controls. And by that, I mean the parameters that we use to control a time step and also to correct the solution as it's solving. The first thing to note that we're using the Pimple algorithm. Now the Pimple algorithm is actually able to deal with what we call a high current number. So without jumping into a rabbit hole, a current number is explained later and is actually a definition of basically how fast a particle can move through one cell in its entirety, and if it moves through too many cells, for example, then you might get some instability. But the Pimple algorithm, if used correctly, can actually negate that. So we're going to try and run this Pimple algorithm with a high current number. And what we need to do is we need to set the relaxation factors. So if you're familiar with the steady state simulation setup, then you can actually get an idea of what these relaxation factors are going to do. If I just quickly skip here and show you a small article that I wrote earlier. Basically, it gives you an in-depth guide as to what's the difference between Pimple and Piso, when to use each one, and in what scenarios you should be using. Generally speaking, if you've got a current number below 1, maybe 0.5, something around there, you might actually find that the Piso algorithm is faster. But if you're having some convergence issues or you're after going for a high current number simulations like we're going to be showing today, then you would be going for your Pimple algorithm. So I'm not really going to dive much more into current number, Pimple, Piso, etc. But I will, when we send out this recording, I will also provide a link to this article as well, which hopefully will help you along your transient journey. But I'm going to hop back into the presentation and just give you the rest of the overview as the simulation setup. So I'm also going to show you this in the on the platform. So don't worry if it's too confusing right now. It will hopefully make sense later. So we've changed the relaxation factors to be below 1. The outer correctors are set to about 20, and the inner correctors are about 5. And what I've actually found is this is a little bit of a magic setup for me. Typically you could add more correctors, but this is quite efficient. And we also add 2 non-orthogonal correctors, so if we've got any poor quality cells in here, we'll be able to cope with that. So I said earlier that I was going to give you a better overview as to current number. So as I mentioned, I like to think of current number as the number of cells a particle could pass through if it was to be given a set time step. So if you said if we thought about a cell in one dimension and we inserted a particle into one side and it hits the other side in one time step, then this would be a current number of 1. And this is a function of the time step, the length of the cell, which is cell size, and the velocity in which that particle is moving at. And what we typically want in transient simulations when we're aiming for high fidelity is to actually keep this below 1. What we typically say is below 1 is where we get good stability. But if we're analysing these large period flows where we can say that actually in some areas where this is going to be a high current number, if in these areas we can say that it's going to be pretty steady, then we can afford to push this current number higher. Of course, the mean current number, we don't really want to go above 1, but certainly for those places and those areas where it is fast, the cell sizes may be small, such in this case it could be around that propeller, in this case we could say that we can deal with a higher maximum current number, but as long as we keep the mean current number to be approximately 1 or below. And that's what we're saying in the simulation setup. So I've got an image of the simulation control here. And I've said the maximum current number we can travel up to is 1,000. So that's a lot higher than the 1, which is set as default, or I think it's 0.5 as default. And if you're going to see some steady kind of steady effects towards the smaller refined areas of the domain, then this is absolutely fine. And that is all I've got really to say on current number. If you've got any further questions, then feel free to ask in the question section. Also, you can reach out to me after the presentation. But I am also going to show you some results based upon changing the current number. So what you would expect is as you increase the current number, you would actually lose some accuracy. So all the time we're making this assumption that in some areas there is going to be steady results. This is absolutely an assumption. So it's up to us as the engineer to decide where the limit is. So we could push it up to 10,000, a million, if your simulation would allow that. But what you've actually got to do is take a step back and go, okay, I'm able to push this simulation this hard and this fast, but am I going to get accurate results out of it? So what you've actually got to do is, if you're familiar with a mesh independent study, is what you've actually got to do is you've got to do a set of results with different current numbers and see where you're going to start losing your detail, where you'll start going to lose your accuracy. And what I've got here is the plot of the coughing man. He's going to cough into a tube. Let me play that for you again. He's going to cough into a tube. It's going to be ejected out of the outlet. Some of it's coming back on himself, but eventually the flow catches up and sucks it back through the outlet. So what I've done here is I've monitored at the outlet what that contamination level is, and I've plotted it over time. And what we actually get is something very interesting. So what you can see is the blue line, which is the highest current number, that's at 10,000, is generally speaking has got similar trend to the other two. However, what you can see is we've started to lose detail. So it starts increasing early. You don't get those little humps at around 0.5 seconds. And generally speaking, it doesn't follow the red and the the red and the black line. So what we need to do is we need to come up with a sensible limit to actually give to our simulation to say that, okay, these results are accurate enough for us. And that's what we could draw from this graph. That conclusion would be, I could be happy with a current number of 1,000. or if I wanted the utmost accuracy, I'm willing to pay the extra core hours, then also we could drop back down to 100 or maybe even lower. Bearing in mind, the lower the current number, the more accuracy we're going to see. But what we'll probably find is there is no significant difference between, say, a current number of 100 and a current number of 10. So we could maybe go for 100, or in this case, I would choose 1,000. And if you're familiar with the with mesh independent studies, this is very much similar to that kind of study. So we're looking at what is the most cost-effective effective scenario in our case. What are we interested in? Can we get the key results from this current number? If yes, then absolutely go for that current number. So what I'm going to do now is I'm going to show you a live demonstration. I'm going to show you the SimScale platform. Let me just hop over to it. And as I mentioned before, it is browser-based. So this is Google Chrome. I'm just showing you the SimScale platform in its entirety. On the left, you're going to see the geometry tree. So if I expand that, we've got one single geometry. And we've got the simulation tree. Hopefully, some of you will be familiar with the SimScale platform. So I'm going to show you kind of the most significant setup parameters. So I'm going to start with the by showing you the geometry. So this is our mixing tank. If I make it slightly transparent, you'll be able to see all the way through the rotating zone, the impeller, the tank itself. And also, if I move on to mesh, we can see that mesh that I showed you before, where if I also make that transparent, you can see a very uniform mesh in the tank itself, and it is only really refined towards those blades inside the rotating zone. And as you can just see on that surface, it's also refined in the cylinder around this to make sure that we capture the flow properties correctly. In addition to this, I've also added some boundary layers. So I've put a boundary layer inflation to make sure that we've got some good wall modeling going on. And in its raw form, that is all you really need to do to set up the mesh, apart from select generate and be returned with the results. So next up is the initial conditions and boundary conditions. So in terms of boundary conditions, this was actually pretty simple to set up. I've put one boundary condition that's called wall. So the wall is a no-slip wall function boundary. I've defined no other boundary conditions at all. So there's no flow going in, there's no flow going out. But there is a rotating zone concept that we've defined to be this cylinder here, and it is rotating at 63 radians per second. And I've also defined the axis in which it's rotating and the origin of that axis. So that's basic setup of a rotating zone. But more importantly is the initial conditions. So we've got initial conditions for the passive scalars, which is the one that's most important here. And the passive scalar has actually been defined to a subdomain. Now the subdomain, if I click it, is the top half of the geometry. So if I just make that solid, you can see that it encloses the top half of the mixing tank, and that a subdomain value of 1 has been assigned as the passive scalar. Everything else is 0. So the global is 0, the subdomain is 1. And that's how we split off one fluid from the other. And then the final things to set up are mainly done in the numeric section and the simulation control section. So firstly, simulation control. Simulation control, what we've done is we've defined an end time. So this is run for 2 minutes. So we're seeing 2 minutes of simulated time is what you saw in the results. And we're going to start off with a delta t of 1e to the minus 5 seconds. So very, very small, just to make sure that we get some early stability in the simulation. If you're familiar with running transient simulations, what you'll find is that you tend to get the instabilities at the beginning of your simulation. If you pass through the first 5% of your simulation, you're probably in a good place. So it's all about getting that initial stability, and then after that you're probably going to be fine. The current number, what we're actually doing is we're saying this is the maximum current number that you're allowed to go. And that's important because when we actually go to solving, if I actually show you a convergence plot, we've got the maximum current number up here, so it actually reached about 700 typically. But that's not to say that it's going to be a current number of 700 everywhere in my domain. So as I said, it's going to depend on velocity, it's going to depend on cell size. So this isn't really a true story to say it's going to be a current number of this everywhere. It's not. This is just in the maximum, so that could be, as I said, around your impeller in this case. The mean current number is actually sitting just below 1 in this scenario at 0.93, and that's really what's given us most of the good results. In this case, we're actually running at a current number of 1,000. I did show you a case where we ran at 10,000. In this case, if we pushed it any further, then we would expect a current mean to be more than 1, and we would start dramatically seeing a reduction in accuracy. So we're going to say that we want the adjustable time step to be set as true. So we're not going to explicitly say that it has to do a time step of 1e to the minus 5 every single time. What we're saying is you can adjust the time step as much as you like, as long as the maximum current number doesn't exceed 1,000. And that's what this parameter means. It says, are you able to change your time step to make it more cost effectively? Because if you were to do the same time step over and over again at a very, very small time step, then that would end up racking up a lot of core hours and a lot of expense to you. What you want to do is minimize this and push it as far as you can without going above a reasonable limit. So just below the maximum current number, we also got to say what is the maximum time step that I'm going to allow you. So I've put 1 second here. Sometimes it might be advisable to set it lower if you're having troubles with stability. So, for example, if you were to have a boundary condition that has a velocity flow inlet that is off all the time, you might set it as 1 second, 100 seconds. It would be quite happy until you turn that boundary condition on. The second you turn that boundary condition on, it doesn't really know what to do with itself. The current number is going to shoot through the roof, and you're not going to maintain that stability. But you might be able to save it if you restrict the time step, say 100th of a second, and then as soon as your boundary condition turns on, you might be able to maintain stability at that time step. But in this case, we haven't got that worry. This is just a mixing case. There's no flow going in or out, and the blade is spinning at a constant velocity. So I've got no risk of shocking the system into instability. So it's absolutely fine to set quite a high number here. The right interval was set at every second. So what that's actually saying to the solver is, how many times do I actually want to see the results? How many times do I want to save those results? And I'm saying I want it every second. So I'm going to get 120 sets of results each second throughout the solve. And what that's allowed me to do is actually analyze the mixing over time. It's allowed me to put it into power view and really get the range of the fluids and things like that. So this is really the level of detail that you want to get out of the solver. And finally, you select the number of processes. So one of the main things about this simulation is we've got two simulation runs. We've got one on 8 cores and one on 64 cores. And if you don't know anything about parallelization or how well a CFD code scales, then a background is that the more cores you throw at a simulation doesn't mean to say that you're going to get a faster solve. So in this case, because we're dealing with a mesh that's so small, 230,000 cells is not a big mesh size. If we solve that on 64 cores, the very fact that we're splitting the domain up into 64 different pieces and sending them to different processors, and the fact that they have to all communicate with each other, is going to slow the simulation down. So when you think you're going to be getting the simulation back faster, what you're doing is actually throwing more money and getting it back a tiny bit faster. And you've got to be able to put a sensible number on these simulations. So typically on SimScale, 8 cores is what I would recommend, up to about 1 million cells. 64 cores, you would only really need to go to 64 cores or -6 cores if you had 30 million cells or 50 million cells, and anything in between. So the idea is not to just pick the biggest amount available to you, but instead put a sensible value on that. And the reason for that is because if you look at the core hour usage for the 8-core version, you can see that it's used 68.7 core hours, running it for 500 minutes. Look at the 64 core one. We've almost solved it, okay, just a bit less than twice as fast. But the core hour consumption was much, much higher. So that was 265 core hours. So 60 something compared to 260 something is a big difference, but you've solved it twice as fast. So it's up to you to decide whereabouts you want to sit in that. Do you want fast results, or do you want cost-effective results, which is the subject of today's topic, really. So this is another parameter that really goes into the fact that, do you want to be running a fast simulation, or do you want it to be cost-effective and efficient? So top tip, sensibly pick the number of cores that you're going to be using for a transient simulation based upon the number of cells in your mesh. And I think one of my colleagues actually a while ago did a little YouTube video telling you how you should choose the number of cores for your simulation. So if you want to be sent a link to that as well, please reach out to me, and I'm happy to pass it along. So finally, we've gone through the numerics, the simulation control. So now it's time for numerics. So numerics, if you didn't want to really understand anything that I'm talking about in this complicated window, you could just take away that if you use 20 outer correctors, 5 inner correctors, and 2 non-orthogonal correctors, that's probably going to give you a good setup to start with. You can choose more or less, but typically this is a really good starting point, and if you don't really want to understand any of the technicalities, start with that setup. The way I like to think of the pimple algorithm is like solving a little steady state simulation, but for every single time step. So if you draw the similarity between the two, then your outer correctors is going to be number of iterations, your inner correctors is going to be kind of just making sure you get stability. And then the same thing with the non-orthogonal correctors. If you've got a really bad mesh, try this first. Normally it gets you out of a tight spot. And then also we've got relaxation factors. So the idea is a typical transient simulation running for 1 outer corrector is always going to be set at 1. If you're running at more outer correctors, so you're going to be correcting it and solving a little tiny steady state simulations, I say, then what you're actually going to want to do is set some relaxation factors so that it's not taking the entire solution as before into your next step. I tend to start for transient simulations at 0.7 throughout. If you're having trouble with stability, then you can lower that, but sometimes you might end up lowering it and still not getting the results you want. And the issue might be an issue elsewhere. So if you're running a transient simulation and you've got some stability issues, I would absolutely encourage you to maybe reach out on the forums or reach out to one of the application engineers, because we do pride ourselves in support, and that we've got quite a few of our application engineers on the chat. You can find the chat just here, FYI. So that's in its essence the numerics and the simulation control setup. What I'm just going to show you is the solver log. So before we start looking at the convergence plots, the results, I'm going to show you the solver log. And this gives you a lot of information about what's happening in Transient. So you've got pimple iteration 1, pimple iteration 2, and you can see the inner correctors that it's performing. And what we're going to do is we're going to scroll down and we're going to see how it's actually doing for each time step. Now in this case what you've got is pimple not converged within 20 iterations. So in this case you've got a choice whether you increase the number of outer correctors. So if you increase the number of outer correctors to 100, would this then converge per time step? So you've got to make that choice, bearing in mind the more outer iterations you do, the less cost effective it becomes. But more importantly, you can actually monitor what the residuals are doing for each iteration and make a decision as to whether this is actually sufficient or not. And in this case, I made the decision that that was actually good enough for me. And in the convergence plot, so we're going to move from the solver log now to the convergence plot. What this does is it shows you the residual at the final time step. So in general, my velocity and my turbulence values and my scalars are all below about 1 e to the minus 2, 1 e to the minus 3. In this case, you could probably add a few correctors if you so wish. But the most important one is the pressure, which is still sticking up there. And what your target will be is to reduce the relaxation factors and increase the outer correctors until this becomes down to what you would typically call reasonable for even a steady state. So if you would expect below 1 e to the minus 3, then that might be your target. Typically you want to see a reduction in about 3 orders between your initial time step, between your initial iteration and your final iteration. And then finally, to kind of show you the results, so the output of this entire process, after we've gone through all these setups, we've gone through all this theory, we really want to know that we're getting a good output. So what we've done is we've put some probe points within the domain that we can monitor over time. So if I just quickly load up, say, the passive scalar, there we go. We can see what it's doing over time, and what I actually had is a probe point in the top half, a probe point in the bottom half, and a probe point midway. And logically, you can probably work out which one's which. And also, just to get an idea of what the forces were on the impeller throughout the solve, I also added a forces and moments control to the impeller itself. So just to show you that you can get all sorts of outputs from these simulations, as long as you're thinking about what you want as an output beforehand, you can really get everything you want really from one single simulation. I'm not going to dive too much into depth with this, but these probe points and force plots can be defined under result control, and you can see them just here. You can just add, say, forces and moments, and then select whatever faces you're interested in. And finally, solution fields. So this is where you're going to get all your colourful pictures and your velocity fields, your vectors, everything that you associate with a CFD simulation. Right on the platform in SimScale is under solution fields. And because this is a transient simulation, it makes for some beautiful animations, which I'm not going to show you on the platform itself because it takes a little bit of time to render, but I've got some pretty cool animations of the results on on the presentation itself. Actually, what I might do is I might just show you the shots that I've taken earlier, and then I'm going to show you the animations actually on the presentation. That'd be much quicker. But if you guys are interested later, we might be able to dive back into it. So this is a velocity plot on the black arrows with the last time step, and we're showing passive scalar. So you can see that you've got an almost not very well mixed zone up here, and as expected, round and under the impeller you've got quite a well mixed undermixed zone. Remember earlier we said we want to be about 0.5 to be fully converged, so that is around these zones here. But we've got some cool animations actually showing you that later. We've got a velocity plot, so the last time step I've said, okay, what if we put some particles in here, what is the path that they would take, and this is the path. As you can expect, it goes back round and into the rotating zone. It's projected up into the mixing tank, but generally speaking it's quite stagnant in the top half, as we would expect if we've got a impeller in the bottom. So I'm going to quickly, being very conscious of the time, I'm going to quickly jump back to the presentation, and I'm going to run you through the last few slides. So what we really want to be taken away from this transient simulation is how well these fluids have mixed. So we can do this by analysing the range of the fluids over time. And as we can see on the left, this is actually visualised in terms of fraction of the fluid. So 0.5 or green is actually very well mixed, and red is not very well mixed, blue is not very well mixed. And we can see how that converges towards 0.5 using this animation over time. And then to see that in 3D, we've got the same graph but a different animation, where we can actually see the contours of the fluid fraction disperse as it's being mixed. And finally, I've drawn some key learnings now. We can see that from these results that actually the scalar is top heavy. So we want it to converge towards 0.5, but actually there's more above 0.5 than there is below. And that's because there's more of the zone that is poorly mixed above the midline mark than there is in the bottom. And this is kind of described by the flow patterns. You can see how this can come about. So where the stagnated flow at the top is not mixing very well, this of course corresponds well when we're actually looking at how well it is mixed. So that concludes the official part of the presentation. Now I suppose it's over to you guys. If you've got any questions, you can ask me basically anything. Okay, I've got a question. Thank you for the presentation. You're very welcome. Do you have any plans for having electromagnetic field simulations in the future? We haven't discussed it as of yet, but of course we're always listening to user feedback. Generally speaking, we use the open foam in the back end. So if we can modify OpenFOAM, or OpenFOAM has some electromagnetic field simulation features, then we could absolutely implement it. It's more about whether the demand is there. So the more people ask for it, the more likely it is to appear in the SimScale platform. And because you've asked, I'll take a note of it to make sure that I add the feedback. Another question. Are there any projects or case studies on SimScale I can have a look at? The answer is yes. If I quickly nip out of this this presentation, so if I go on to public projects, basically there's a huge range of public projects available to you. If you wanted to look at something specific, say if you wanted to look at something aerospace or architectural, or even analysis type specific, then you could, of course, select one of these down here. If you wanted to search for something specifically, then you can just search in that function. I personally have got this webinar project available to you, and also that coughing simulation. I've got that available as a transient simulation that you can use as a setup. Additionally, there are other transient simulations that my colleagues have done that you could use as a setup for different types of scenario. So depending on your application, there should be something here for you that you can use, and if not, feel free to ask in the forums. There is an amazing amount of wealth of information there, and they might have something hiding up their sleeve as well. Okay, so SimScale platform, the question is, I'm interested in simulating heat distribution of electronic boards. Do you have a kind of API where we could set up and run simulations without the need for the user to interface with the platform? So firstly, absolutely no problem with the heat transfer type of simulation. We've got the conjugate heat transfer analysis type, but we don't at the moment have any way of going into the back end of SimScale and automatically defining that from an API. We do, however, recognise the need for it. I think, unfortunately, not today, but certainly in the future that might be a possibility. Certainly, with a lot of larger companies using simulation and CFD, that is a requirement. So it might become available in the future. And if you want to reach out to marketing, then that would be great, because what they can actually do is keep you up to date with any of these requirements that you might have. So if one day that we decide to launch these features and you haven't been following the news on SimScale, which is absolutely fine, then we can reach out to you and just say, hey, do you know we've released this? Are you interested? So feel free to reach out to our marketing or sales team. Thank you. Okay, so I haven't got any more hands up. If you are asking or typing a question, then if you could just raise your hand again, that would be great. Otherwise, I think I'm going to conclude this webinar. This will be, of course, recorded. This has been recorded. It will be sent out to you, along with the link to my document about the transient setup, about Pimple, PISO, and the Courant Number, etc. So you can read that as well. But unless there's anything else, thank you very much, guys. Cheers.